Now, we're back with different numeration systems. So, these are the ones I was trying to prepare you for. So remember that last time I took our basic numbering system and I pulled it apart and we wrote it almost in scientific notation with powers of 10. And the reason for that is for what we're getting to here. So now we're looking at different numeration systems. Now, what we did last time, so I'm just going to start with our basic, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Even though we don't, we could call this base 10. And the idea is that there are 10 digits that we can use, 0 through 9. So this would be base 10. Now, there are other bases, and that's what we're looking at here. So let's see, I don't want to start you off too ugly. Let's go with base 4 to start off with. Now, I don't know why you'd want to represent numbers in base 4, but let's say you were that nerdy and you wanted to represent numbers in base 4, we could do that. So in base 4, the thing to understand is that there are not 9 digits like we have. There are only 4 digits, 0, 1, 2, and 3. So there are 4 digits going on here. Now another way to remember base 4 is the idea is division. If you were to divide any number, let's go with 43. Divide any number by the base. So that goes in there one time, leaves us a 4, and then we end up with a 0, right? Goes in there 0 times, and that leaves us with a remainder of 3. This is what we're focusing on. When you look at base 4, the different remainders that you can get when you divide, long division, not in your calculator, but long division, are 0, 1, 2, or 3. So this is the remainders that are popping out. And again, think about that. When you divide any number by 10, these are the different remainders that pop out. So instead of starting to think about them as, oh, those are my counting digits, think about them as remainders. So if we're going to deal with base 4, that means that instead of looking at powers of 10, we need to focus on powers of 4. So we're not using 10 to the 0 and 10 to the 1 and 10 to the 2. We're using 4 to the 0. And remember that anything to the 0 power is just 1, so that'll just be 1. Then there is 4 to the first, which is just 4. Then there is 4 squared, which is 16. Then there is 4 cubed, which is 64. And I honestly don't know. I don't have that guy memorized in my little brain. So 4 to the 4th would be 64 times 4, which would be 256. Now, what we're going to do is we are going to use that expanded form and these 4 digits with the expanded form, but instead of using powers of 10, we're going to use powers of 4. So watch the way that I'm going to write a number. So I am going to say that we have the number, let's go, do I have something written down? I might as well use what I have written down. Base 4. So let's say we have 2 times, oops, see right off the bat I want to go to 10, but we're going to go 4 to the 3rd plus 0 times 4 squared plus 3 times 4 to the 1st plus 3 times 4 to the 0. So here is expanded form. The issue though is that these are not powers of 10, they are powers of 4. And because they're powers of 4, it means that this is not pretty, it's ugly. Again, I don't know the reason why someone would want to use powers of 4, but if they did, it would be ugly. So what we want to do is we want to represent this number in a number of different ways. So this is written here. If we want to really write it as base 4, then the number would be take off the powers of 4 and just use the digits out front 2033. Now, don't say that as 2033. It's not 2033, it's 2033. And then I'm gonna hit it with a little subscript of a 4. And that little subscript, actually, are we writing it with 4? No, we're writing it out, sorry. 4, sorry about that. So it's a little subscript of the word 4, not the number 4. And what that's telling people is that this number is in base 4. It's not the number 2033, it's 2033 in base 4. If we want to figure out what the number actually is, what we need to do is actually calculate this out, right? So we need to take 2 times 4 cubed. So we're going to start with 2 times 64 plus, now the nice thing about this one is it goes away, doesn't it? So we don't need to worry about that. Boop. Then we need 3 times 4 to the first, which would just be 3 times 4. And then we need 3 times 4 to the 0, which is just 1, so that's just a 3 on the end there. Now remember order of operations, we're doing each little piece separately. So 2 times 64 would give us 128 plus 12 plus 3. And then if we add that all together, I suppose I could do that real easily, but what the heck, I have my calculator. Oop. Except I forgot how to add. That's better. We end up with 143. Now, I'm gonna write a little base 10 because this is now our number 143. But the number 143 is represented as 2033 if we were in base 4. See how kind of weird that is? Okay, I definitely think it's weird. If you think it's weird, we're on the same page. Okay, so since we're still dealing with base 4, let's stick with base 4 for a little bit longer. Let's say that I gave you the number 103221, and I put a little 4 underneath it like that. Okay. All right, so that's telling you it's in base 4. Again, that number is not 103,221. This is 103221 in base 4. But I don't want it in base 4. We don't read base 4. I want it in regular base 10. So what we're going to do is we're going to do what we did over there. So the idea is to remember that that's 4 to the 0. This would be 4 to the 1, 4 to the 2, 4 to the 3, 4 to the 4, 4 to the 5. And the way that I do this is I do it right underneath it like that. And that way you don't have to write out this whole extended form thing over and over again. So what we need to do is we need to figure out what 1 times, so we're going to do a little multiplication here, 1 times 4 to the 5th. Now 4 to the 5th is not on my list, so let's see what 4 to the 5th is. 4 to the 5th is, add it to our list here. 1024. So 1 times 4 to the 5th is 1024. Plus 0 times 4 to the 4th, we can leave off, can't we? It's not, doesn't affect us at all. Now we have 3 times 4 to the 3rd. So we need to do 3 times 64. 64 times 3, boop. That's 192. Now we need 2 times 4 squared, or 2 times 16, which is 32. Then we need 2 times 4 to the 1st, or 2 times 4, which is 8. And then we need 1 times 4 to the 0, or just 1. So again, basically what I'm doing is skipping the step of writing it like that. I'm writing it vertical. So 1 times 4 to the 5th, 0 times 4 to the 4th, 3 times 4 to the 3rd, and it just saves you a step. So let's see, we go 124 plus 192 plus 32 plus 8 plus 1. So in base 4, it was 103221. But in our regular base 10, this is 1,257. So that's the same number represented in two separate bases, okay, 10 or 4. Now, the other thing that we need to be able to do is we definitely want to be able to look at a number like this and turn it into a power of 10 so that we can understand it. But it is possible that we might want to go from the base 10 and turn it into base 4. Again, if you love base 4, you want all your numbers in base 4. So let's rewrite in base 4. All right, so let's see. Let's go with the number, let's go 137. And I'm gonna put the little 10 on there because this is truly in 10. So the way that we're going to do this is we're gonna look at this number. Actually, no, I don't like my number. Yeah, let's change it. Sorry about that. Let's just change it to 73. 173. Let's do that instead. Sorry. Okie dokie. Now we're gonna take this number and we're gonna compare it to our list of 4s if we wanna go to 4. And we're gonna notice that 256 is bigger than our number, yes? So that means that we're gonna start with 64. So what I want to do is I want to figure out how many 64s are in that number. So basically it's like dividing by 64. So if you take 173 and divide by 64, we get 2.7. So there are two 64s in here. And I'm gonna write that as 2 times 4 to the third. But the problem is that it's not perfect, is it? It said 2.7. So I wrote that there are 2 times 4 to the third, but there are some leftovers. So if we go 2 times 64, we get 128. So in order to turn 128, in order to get 128 up to 173, we need to see what the remainder would be. 173 minus 128. So we're gonna go plus 45. So this right here is another way to write the number 173. 2 times 64, which is 128, plus 45. Now, I know it's kind of like it's all this addition, or it's all this subtraction and division in your calculator, or by hand if you want, but that's what we're looking at here. Now, the next thing we're gonna do is we're gonna take this 45 and we're gonna move it down here. And now what we need to do is using the next guy in the list, the next guy down, we need to figure out how many 16s are in 45. So 16 plus 16 is 32. So there are 2 16s, or 2 4 squares. But if this equals 32, then what, again, is the leftover? So 45 minus 32 is 13. So 45 can be written as 2 times 4 squared, 2 times 16, plus 13. So again, it's all this remainder going on here. So I'm going to bring the 13 down here, bring this remainder over here, and now we're looking at the next guy in the list. So the next guy was 4 to the first, or 4. So how many 4s are there in 13? Now hopefully we're getting into numbers that we are familiar with. So would everybody say that there are 3 4s in 13, right? 3 times 4 is 12, with a remainder of 1. And then finally, we're gonna say 1 equals, and the nice thing about this last one is it's just gonna be that particular digit, whatever it was. So that last step, you can't forget to do it, but it's not any real mathematical work. So what we end up with is the number 173 in base 10 is actually the same as 2231 in base 4. And we got that by taking those numbers off of the front. So again, instead of horizontal, it's written vertical here. But but that's all we're looking at, 2, 2, 3, 1. Okay. All right, I'm gonna change bases on you. Okay, we've done enough with 4. I want you to be aware that there are other ones. So I want to show you one, just so that you can see. We can use things like base 11. So base 11 would mean that we have 11 digits useful to us, but there's a problem with this. That would include our 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but then there's one more digit, and we don't have one more digit, so we use a capital T for 10. So you can see that if you're using larger bases like base 11, all of a sudden your numbers are going to start having different values in them. So that's a royal pain in the butt. But here's what this might look like. We might see, and I'll just use a small one. We don't need to go big here. But maybe we would see the number 6T5, and then it would say 11. 6T511. Ay, ay, ay. So you go, wait a minute, that's no number I've ever seen, and it's not, because who uses base 11? But apparently you can. So now the idea here, base 11, switch gears. Are we using powers of 4? No. Are we using powers of 10? No. We're using powers of 11. So this guy would be 11 to the 0, this guy would be 11 to the 1, and this guy would be, not 10, stupid. See, even you get used to 10, 11 squared. So if we wanted to write this number out, it's going to be 6 times 11 squared plus t. Now in our numbers, what does t represent? T represents the number 10 times 11 to the 1 plus 5 times 11 to the 0. So 11 squared is 121. So 121 times 6 equals 726 plus 10 times 11, which would be 110, plus 5. So altogether we get 726 plus 110 plus 5 equals 841, and this is in base 10. So in our numbers, that's what we get, okay? So the number 6T5 in base 11 is the number 841. See how weird this can get? Now, you might be sitting there going, what the heck? Why are we using this? This is so stupid, I don't want to do this ever. But let me tell you, me giving you this lecture in this form, you watching this on your phone or on your computer, you sending text messages, you turning your papers in digitally through the internet, all uses this type of situation. Because when it comes to a computer does not use base 10. So in computer language, the computer uses what we call binary, and binary is just another name for base 2. So the computer does not use base 10. Luckily, it doesn't use base 11 either. The computer uses base 2, which means in base 2, there are only 2 digits. And the only 2 digits there are 0 and 1. So if you divide any number by 2, you're either going to get 0 or 1. Or, sorry, as a remainder. The number goes in, and as a remainder, there will either be 0 or 1. If it's an even number, you're going to get a remainder of 0. If it's an odd number, you're going to get a remainder of 1. And this is the way computers work. So we definitely, while we might not ever use binary in our everyday life, I mean, I certainly don't use binary myself, like writing it out, but every time I turn on that phone or that computer, I'm using binary. And that's why we learn this, just to see how the world works and how the world has progressed. So, first thing, when we're in base 2, we need to realize that we're looking at powers of 2. So let's make a list of powers of 2 over to the side. So 2 to the 0 is 1, right? Anything to the 0 power is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. 2 to the 6th is 64. 2 to the 7th is 128. 2 to the 8th is 256. 2 to the 9th is 512. And 2 to the 10th is 1024. Now, it's very possible that you might have to go further, okay? But hopefully not too much, okay? So, but this list, now again, it's not nice powers of 10, okay? It's not. But at least it's not with T's and all this 11s and 4s and stuff. At least 2 is kind of a nice number, right? Even or odd type thing. But this is what a number is going to look like in base 2. So you're going to see a number that looks like this. 1, 0, 0, 1, 1, 1, 0, 1, 0. Because there are only 2 digits, every number in base 2 is just going to be zeros or ones or some arrangement of that case. So every number looks like that. And again, the idea is the computer likes that, because what that means is it's either kind of like a right or wrong. You either do it or you don't. Do it or don't. It's even or it's odd, right or wrong. There's no extra digits running around there. Now, for us, it's like, what the heck? So what we want to do is do the same thing we were doing before. I want to figure out what this is in base 10. I don't know what number that is. So let's put it into base 10. Now, just like we did before, we're going to start with powers of 2 this time, and 2 to the 0 would go first. So 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7, 2 to the 8. Okay, so we're not going all the way to the top here. Okay, we're not going all the way. We're only going to this point here. Now, the nice thing about this is that there is either a power of 2 or there's not. So in this case, we have 1, 2 to the 8th. So there's no real multiplication. You just have to say that there is a 256. Okay. So there's one of those. Are there any 128s? No. Are there any 64s? No. 0 64s. But there is 1 32. Then there is 1 16. Then there is 1 8. Are there any 4s? No. Are there any 2s? Yes, there's 1 2. And then there's no single digits at the end. So the nice thing about this is every time you see a 0, you just leave it off. But every time you see a 1, you just write down the corresponding number in the list. There's none of this crap where you're going to have all these weirdo numbers. When you go to expand out your base 2, it's always going to include those numbers. Always, always, always. So now we just need to add those guys together. 256 plus 32 plus 16 plus 8 plus 2. And I get the number 314, and I'm going to stick a little base 10 on there to remind us. So in base 2, it's 1 0 0 1 1 1 0 1 0, but in base 10, so the way that we would see it is 314. So if you type in the number 314 into your calculator, the computer chip in your calculator immediately changes it to 1 0 0 1 1 1 0 1 0. Isn't that weird? That's the way it works. Okay, so let's look at another one here. So let's say we had 1 0 0 0 0 0 1 1 0 1 in base 2. So let's see what this guy looks like. Now again, this is going to be a 2 to the 0 But I'm gonna leave off the ones we don't need. We don't need this guy, do we? So I'm gonna just kind of, instead of making it all cluttery, but we do need a 2 squared and a 2 cubed, right? Then 4th, 5th, 6th, 7th, 8th are gone. Everybody agree? So that means this would be a 2 to the 9th, right? Make sure that we've got that. It's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's the correct power on that too. Okay, so this time, again, because of these zeros, we know we can just kind of leave them off. So now all we need to do is just slide through and write down the guys that we still have. So the 2 to the 9th is the 512, plus 2 cubed is 8, plus 2 squared is 4, plus 2 to the 0 is 1. So you see how it actually, if you have that list over there, this actually starts to get quicker. 512 plus 8 plus 4 plus 1. So this is the number 525 in base 10. Good. Okay, now let's go the other way. Let's rewrite in base 2. Go to base 2. Okay, I'm going to start us off small and then we'll get a bit bigger. So let's say that we have the number 18. Okay. Now you're going to see, because of this only 0 and 1 thing, this gets a little bit tricky here. So we've got the number 18. So again, what we do is we go to the numbers in the list and we see which one would fit into 18, and that would be 16. Everybody agree? So we're going to say that 18 is equal to 1 times 2 to the 4th. 1 times 16. And then what's the remainder? The remainder is 2. Okay. So then we write down 2 here. But here's the problem. And this is why I wanted you to see this, is that we don't immediately get to jump all the way down to here. We need to figure out, if we started here, we need to cycle through all the way down. So can we divide 2 by 8? We can't, which means there are 0 8s in this number. Can we divide 2 by 4? We can't. So there are 0 4s in this number. Then finally we get down to this one. Okay, so we're cycling down through them. And so how many 2 to the firsts are in there? Just 1. So this is 1 times 2 to the first. Don't forget your 0. So remainder 0. Now we're not done with the cycle, so we have to go 0 equals, and now because it's 0, that just means it's still going to be 0. Okay, but we run our way through the whole cycle. So we do not get to just skip around. We have to keep placeholders. So the number 18 in base 10 is actually equal to the number 10010 in base 2. So 18 is 10010. Okay. Now, can you see how tedious this would be if you had to actually write this out in everyday life? You'd have to remember which placeholder was which. Okay, so let's do another one of this type here. So let's say that I gave you the number 633. So 633 in base 10. Come over to our list, and it means that we're going to start here, right? This is too big, so we're going to start here. So 633 can be written as 1 of the 2 to the 9ths. Okay, so it's 1 2 to the 9th. But what we need to do is we need to figure out what the remainder is. So if you take 512 away from 633, we end up with 121. So we put 121 over here. Now remember though, we have to cycle through. So the next guy down would be the 2 to the 8th. But are there any 256s in there? This is too big, isn't it? So it doesn't mean we skip it. It means we write 0 times 2 to the 8th. And then we write 121 again. We move down to the next guy, which is 128. Darn, still just a teeny bit too big. So that's another placeholder, another 0 times 2 to the 7. Write it down again. Okay, now, there is a 64 in 121, isn't there? So there is 1, 2 to the 6th, 164. So what we're gonna do is 121 minus 64 to see what's left over. And what's left over is 57. Now the 57 comes over here and we start the process again. So we were just here. Now, in the number 57, is there a 32? There certainly is. So we're looking at a 1 times 2 to the 5th. But again, we need to see what our remainder is. So 57 minus 32. Whoops, I hit the wrong button. 57 minus 32. This gives us 25. Okay, then 25 comes over here. And we move to the next guy on the list. Now, are there any 16s in the number 25? There is. There is a 16 in 25. So 1 times 2 to the 4. And again, we need to see what's left over. 25 minus 16 is 9. Okay, slowly but surely, we're getting there. 9 equals, now we're here. Is there an 8 in 9? And there is, isn't there? So there is 1 of the 2 to the thirds. Now, what's left over is just a 1. Everybody agree? Now we're not done. Put the 1 over here. But remember, in the list, we gotta go all the way down, and we're here. So are there any 4s in the number 1? Can we divide 1 by 4? We can't, can we? So there are 0 of the 2 squareds. Stick with 1 again. There are also going to be 0 of the 2 to the first, right? There's no 2 in 1. We can't do the division there. And then finally, there is 1 times 2 to the 0. And we are done. Okay, so that was a long process. Real pain in the butt, but a long process. Now remember that what we're looking for is these guys right here. That's the number. So even though it's vertical, we say 1 0 0 1 1 1 1 0 0 1. So the number 633 can be written as 1 0 0 1 1 1 1 0 0 1. Oh, look at that. It's a palindrome, right? Backwards and forwards, it's the same. So 633 is kind of a special number in binary. That's cool. I didn't know that when I wrote that up there. Anyway, the things that math people find nerdy or important, it's kind of nerdy. Right, you get the idea here? Okay, so remember, you're either going to powers of 10 to regular, or you're taking a number from 10 and going into a different power, or a different base, a different base. Okie dokie. So give that a go, and we'll see how that goes. All right, good job.